Our next major goal after the Urison lemma is another theorem which lets us construct real valued functions. But to keep things encapsulated, to keep mind focused on one thing at a time, we will first just see some things about uniform convergence, which are important but should not be new in the sense that they're essentially identical to what you would see in analysis. So now suppose we have Fn, so let Y be a metric space. And X is a topological space. So Y is also a topological space using the balls as the neighborhood basis and hence as the basis. So X is a topological space. So definition is a sequence Fn. All of these are functions from X to Y, or functions converges uniformly to F X to Y. Again, converging, the simple way of converging is that each little x it converges to y. That would be pointwise convergence, which presumably everyone has seen, both this and uniform convergence. But we'll anyway see pointwise convergence when we talk about the product topology. So let's just look at the non-trivial thing here, uniform convergence to this. Remember, Y has to be a metric space. In the application, we'll see it will be actually just R itself, F from X to Y, if for all epsilon greater than 0, there exists n in n such that n greater than n implies that distance that the distance, and I'm going to write it d infinity of f n and f, which is less than epsilon. And what is this? Where this is the supremum. D infinity of fn and f is supremum of n x in x. I could write it directly as a supremum of a set. It's the supremum of the distance between fn of x and f of x. In general for f and g, so it would be nicer to write it that way. So where d infinity of f and g is the supremum of the set of the distances between f of x and g of x for all x in R. And now this distance, where is this? F of x and g of x are in Y, which is a metric space. So it's the distance in Y between f of x and g of x. This could be infinity, but when we are giving a bound on it, it means it's finite. Okay, so that is what we have is for all. So we don't need this definition. We could simply spell it out as saying for all x in x, dy of fn of x and f of x is less than epsilon. So the capital N doesn't depend on x. That is where the uniformity comes in. And just as in analysis, we have the theorem. So if functions just converge at a point, if each one being continuous does not tell you the limit is continuous. But for the case of uniform convergence, it turns out that a uniform limit of continuous functions is continuous. Okay, this is quite non-trivial and interesting, but is probably something people have seen in analysis, so I will go through it somewhat quickly. I mean, we'll be formally complete, just not motivate too much. So here's the point x, fn goes to f, and f itself is continuous. Yeah, so suppose fn is continuous for all n, and fn converges to f uniformly, then f is continuous, for which we have to show it's continuous at each x. Okay, so let x belong to x be given, and epsilon greater than 0 be given. So what we have to show is if we take points close enough to this, the value of f is going to be close enough to this. So the idea is that value of fn, it looks a little far here, but if n is large enough, the value of fn at this point x is going to be close to the value of f at the point x. And if I take a near enough point, the value of fn at that will be close to the value of f at that. And meanwhile, fn and f are close to each other. I mean, fn at these 2 points is close to each other by continuity of fn. Okay, so let epsilon greater than 0 be given. So but we have 3 pieces here, so we should take epsilon by 3. By uniform convergence, we need a little less. We just need uniform convergence of a subsequence. Okay, so there exists, let's say, capital N in N, such that for all, or let's call this x naught, because I want x as a free quantifier. X naught is your fixed point. So for all x in x, fn of x, the distance in y of fn of x and f of x is less than epsilon by 3. Actually, you can find a capital N such that this is true for all n greater than that, but we just need one n. Okay, which will be capital N plus 1 if you took the definition here. And now once we have this, there exists this as fn is continuous. There exists u open such that x0 in u, and x in u implies that fn of x, distance between fn of x and fn of x0 is less than epsilon by 3. So we are using continuity of fn at x0. Take a ball around it, and you can find an open set which maps into this ball. Okay. Hence, if x belongs to u, distance in y between f of x and f of x0, this is less than 3 terms. There's distance between in y, between all distances are in y, between f of x and fn of x, plus distance in y between fn of x and f of fn of x0. We're using the triangle inequality here, and the third term will bring us back, fn of x0 and f of x0. And now by uniform convergence, we have a control over both of these. So this is less than epsilon by 3. Now continuity gives you epsilon by 3 here, and uniform convergence again gives you epsilon by 3, okay, which is epsilon. So if your sequence of functions converges uniformly, then the limit is also continuous. Okay, so we will be using this to construct a function as a limit. And as you may have seen in analysis, well, when you construct a function as a limit of sequences, it's actually really limit of partial sums of a series. And that's more or less what we'll be doing here. We'll be taking successive approximations to a function, and these successive approximations are sums g1, g2, g3, where the gi's are going to be decaying.